So we will discuss an important concept called displacement function or model, which is very much useful in analyzing any structure using finite element method. So displacement function is defined as they are the functions representing the displacements at different points in an element in terms of coordinates. So that means, just to understand the definition, I have considered an element here. 1, 2 is the element here. 1, 2 is the element, and P is a point on the element. Now, due to the application of loads, this node 1, so these 1 and 2 they are called as the nodes. So nodes are the endpoints of a member. So here, due to the application of the loads on this element is nothing but a part of a structure, maybe a truss member, or I have taken truss element here. So in trusses, you know that the behavior is axial behavior. So tension compression forces will develop in trusses, whereas bending moment and shear force will develop in beams. So here, U1 and U2 they are called as the nodal displacements, because 1 and 2 are nodes. Due to the application of the load, external forces on this element, the nodes will displace. Nodes will be displaced. So U1 and U2 they are the displacements. I have shown, of course, towards right. That means displacement has taken towards right. So if you know the nodal displacements at 1 and 2, you can always find out the displacement at some other point on the element. I have taken that point as P here. P is a point here. Of course, it is a one-dimensional element. I have taken linear element, one-dimensional, only in x direction. So if I take this as the origin, x is equal to 0, and this, if I take it as x is equal to L, so this P can be x is equal to L by 2 or L by 3, whatever it is, in between 0 and L. So you can always find out the displacement at P as UPX here in terms of U1 and U2. So that is why, if you know the nodal displacements, you can find out the displacement at any point in the element using this displacement function model. So here Ux and U1, U2 they are related through one function called interpolation function or shape function. So the shape functions they are denoted by capital N. So if you know the nodal displacements, you can find out the displacement at any other point in the element using the shape functions or interpolation functions. So to understand more precisely, I will consider a bar or a truss or a beam element. So your displacement functions can be written like this: displacement function or displacement model in terms of polynomials. In terms of polynomials, it is the easiest way of expressing displacement functions. So u of x is equal to a1 plus a2x plus a3 x square plus a4 x cube plus etc. up to am x power n. Similarly, v of x, so this is the displacement in the vertical direction, this is displacement in the horizontal direction, x and y directions. So v of x can be written as b1 plus b2x plus b3 x square plus b4 x cube plus etc. bm x power n. So here ux is called as the local axial displacement. Axial displacement takes place in the x direction, which is denoted by u. V of x is called as the local transverse deflection. So transverse means it acts perpendicular to the axis. So if this is x-axis, so transverse to that, so perpendicular to that. So in the lateral direction, whatever displacement is there, that is called as deflection. So here we call it as displacement, here we call it as deflection. So this is also a function of x. So because I have taken only a one-dimensional element. In the case of one-dimensional element, you have only x term. So this is how this can happen in the case of a beam element, whereas this can happen in the case of a truss element. So due to the application of the development of bending moment, due to the application of the transverse nodes, the beam bends like this. Here 1 and 2 once again they are the nodes. At any point P, you can always find out the transverse deflection. Now here in this expression, this A1, A2, A3 etc. and B1, B2, B3 etc. they are called as the generalized coordinates. So you have to remember the wordings here. They are called as the generalized coordinates, where this n is the number of degree of polynomial. So here, if you take up to 2, 3 terms if you take, then n is equal to 2. So polynomial degree will be highest will be 2 here. If you take only 2 terms, n is 1 here, like that. And m is the number of generalized coordinates. Actually, if you observe here, number of generalized coordinates will be 1 more than the degree of polynomial. That means m is equal to n plus 1. So if you take the first case, wherein for a linear element, if you take only 2 terms, a1 plus a2x, only 2 terms if you take for ux, then in this case we can see that n is equal to 1 here, because highest power of x is 1. So degree of polynomial will be 1, and m is n plus 1, that is 2. So m is 2 because there are 2. So these are the m terms, that is a1, a2. There are 2 terms, whereas n is 1 here. Now suppose if you take a 2-dimensional element. So 2-dimensional elements normally we observe in slabs and plates. So where both you will be having x and y directions. In such a case, the displacement model can be assumed using these polynomial functions. You can see here u of x, y. So instead of x, you are going to have x and y both here. a1 plus a2x plus a3y plus a4x square plus a5xy plus a6xy square plus etc. So you can see similarly in the transverse direction it will be same, repeated same, but instead of a1, a2, a3 you will be having b1, b2, b3 like that. So this is how you have to write for a 2-dimensional element the polynomial displacement model. So in that you can discuss some types here. So first one is constant strain triangular element, CST element. So CST, constant strain triangular element. That means at all the points in the element, the strain is constant. So you take any point. So for example, I have taken a triangular element here. This is a triangular element wherein I have shown only one point 1 there. So the strain throughout the element it is constant here. In such a case, so your u of xy will be a1 and v of xy will be b1. That's all. That means they are constants. Please note that these two are constants. So at all the points within the element, so the strain is constant. So this is, in this case you can see that n is 0 here because there is no x term. It is only constant term. N will be 0, but m will be n plus 1, which is 1. 0 plus 1 is 1. So only one term is there. If you take linear constant strain triangular element, that means strain varies linearly. So you have to understand here. So strain varies linearly. So if this is the case, then x term will be there. Linear means x term will be there. So in such a case, your displacement function you can assume as u of xy is equal to a1 plus a2x plus a3y. So first 3 terms will come. And v of xy also first 3 terms will come. So square term will not be there or xy term will not be there. So here in such a case, the thing is at these 3 points, at these 3 nodes, 1, 2, 3, they are the nodal points here. So the variation of strain will be linear. So if you know the strains at these 3 points, nodal points or displacements at nodal points, you can always find out the displacement at any other point, required point using this relation. That is the meaning of that. So any point you can take. So you for example, if you take point P here with coordinates x and y, by knowing x and y and by knowing these constants a1, a2, a3, b1, b2, b3, you can always find out u and v values at this point P. That is the meaning. Next, the third example is quadrilateral element. Once again, constant strain quadrilateral. So constant strain means once again I will take only one point. So wherever you take in the element, the strain is constant. Here also we take u of xy, v of xy as constants a1 and b1. So these two are constants now. Similarly, just like your triangle case, so here also n is equal to 0, m is equal to 1. Linear quadrilateral element. So see the difference here. So linear triangular element, you have this as the displacement function. Linear quadrilateral elements you will be having 4 terms. So you will be having 4 terms. So 4 terms means a1 plus a2x plus a3y plus instead of x square I will take this term because it should be symmetric. It should be symmetric. So A for xy term will come. Similarly for V also, you have B1 plus B2x plus B3y plus B4 xy term will come. So in such a case, you will be having 4 nodal points, 1, 2, 3, 4 for 4 nodal points. So n value will be 1 here. So because the highest power of x, either for x or y, highest power is 1. So here x power 1, y power 1, x power 1, y power 1 like that. So highest power is 1. That is called as the degree of polynomial. That is 1 here, and m value is n plus 1 as usual. It is 2 here. So this is how we can write the displacement models for different types of elements, maybe one dimensional or two dimensional. That means the shape function, this is the basis for obtaining shape functions. So shape functions are the functions, or interpolation function are the functions through which we can obtain the displacements at any point in an element by knowing the nodal displacements. So that is the reason, because normally in the case of structural analysis, so you may be having a truss something like this. So if you have a truss like this, you may be interested in finding the nodal displacements. So first we can find out the nodal displacements. So these are the nodes. So by using the matrix methods of analysis, you can find out the displacement at these nodal points, maybe by stiffness method or flexibility method. After that, if you want the displacement at some other point, let us say I want the displacement here at this point. These are the nodes 1, 2, 3, 4. These are the nodes. And if I want at this point P, what is the displacement? Then we have to use this shape function or interpolation function to get the displacement at P. Similarly, in the case of beams, so you will be having a fixed beam or a continuous beam or a simply supported beam. So here also, this beam may be having different nodal points like this. If at all I want the nodal displacement at point P somewhere here, by knowing the displacements u1, u2, u3, we can always find out the displacement at P. So this is how this shape function or interpolation function is useful in finite element analysis. So in matrix method of analysis, we are going to find the nodal displacements. After next step, if you want some other point, the displacement value, then we have to develop the shape functions and using those shape functions, depending on the type of the material element, so we can always obtain the displacement at the required point by knowing the coordinates of the point.